Alright guys, so let's do a quick refresher of KSP, and this is going to lead into selective precipitation or fractional precipitation, you may hear as well. So KSP, remember, is the solubility product constant. It looks at how much of an insoluble salt will dissolve. So it looks at the dissolution of insoluble ionic salts. So in reality, a salt, even though it's insoluble, some of it is going to dissolve. It's just majority of it will stay in that solid form. So remember, these are set up just like other K equations, where you have the products on top, reactants on the bottom, coefficients become exponents. So here is an equation for magnesium fluoride's dissolution into magnesium ions and the two fluoride ions. And where we're looking at KSP, remember, K equations do not include solids or pure liquids. So we would have our products, the magnesium and the two fluorines. So it would be the magnesium and fluoride would be squared. The magnesium fluoride would not show up in our K expression. So we would not even have to have any factor on the bottom. And this is typically going to be a set number at that specific given temperature. And like we've done in problems yesterday, this is either going to be a value that is given to you, or it is going to be a value that you are solving for. In comparison to that, if we have calcium phosphates, phosphates are insoluble except for the snack ions, so the group 1 ammonia, things like that. So here we have the dissolution. It produces 3 calcium ions and 2 phosphate ions. So when we put that into a K equation, our products go on top, so the calcium will end up being cubed because of the coefficient of 3. Phosphate will be squared because of the coefficient of 2. Sorry, my exponents aren't as high as I would like them. And then calcium phosphate, because it's a solid, is not going to show up in our K equation. And yet again, this at a given temperature, we do have value tables in our textbook, but this is something that will either be given to you or it is something you are solving for. So this is a substance that would have a KSP value of 2.07 times 10 to the negative third. So remember, when we are looking at KSP values, all of our exponents are going to be negative because not a lot is going to dissolve. Generally, the closer to 1 a KSP value is, the more soluble that salt is. So when we're comparing these two, the calcium phosphate is much less soluble because that does have that higher negative exponent. So less of it will dissolve at any given temperature. So like we said, the larger values, the one closer to 1, is comparatively more soluble than another KSP value that is further away from 1. So here are just some common insoluble salts, and you can see their relative KSP values. So something like the lead 2 sulfide with its to the negative 29th is much less soluble than something like lead 2 chloride that is to the negative 5th. So we can actually compare these to each other. So knowing that salts do have different degrees of solubility, that is going to lead us into selective precipitation. And like I said, this might also be called fractional precipitation, where if we had a mixture with different ions, we could precipitate some of the ions and leave the others in solution, is what we're going to be looking at. So this is typically used whenever we have a separation of metal ions in aqueous solution together. We would find an anion that will precipitate with one or both of those metals, and we would have to figure out what amount would allow one metal to precipitate while the other one would remain in solution. So we add a reagent that forms a precipitate with one of the ions but not the other. So that is an option where one of them is soluble, the other is insoluble. So, for example, if we had a solution with both barium and silver, it says we would add silver or sodium chloride, Y. So if you look at the rule for chlorides, remember chlorides are soluble except for PMS, the lead, mercury, silver. So barium chloride would be aqueous, whereas silver chloride would be solid. So that would allow one of the metals to precipitate out of solution. The other metal would stay in solution and be still existing as ions. So it would not actually change what we're looking for. Our other option is we can precipitate one salt over a certain concentration range. So we might use an anion that is insoluble with both cations, but one of them is going to be more insoluble than the other. So that can allow one of the substances at a certain concentration to precipitate, and the other one that is more soluble will remain in solution. So here is an example with some of the selective precipitation. Here it says we have a solution with lead 2 and magnesium 2, concentrations equal to 7.0 times 10 to the third molar. And it wants to know over what range of fluoride can a selective precipitation occur. Both of these, whenever you look at the rule for fluorides, we don't use this one too often, but fluorides are fairly insoluble. And for these two specifically, their KSP values. Lead 2 fluoride has a KSP value of 7.0 times 10 to the 7th, and magnesium fluoride has a KSP of 7.0 times 10 to the -11th. So if we're looking at the equation for the dissolution of both of these, oh, excuse me, I'm getting ahead of myself. So we're looking at what salts are we talking about precipitating. So that is going to end up being, we're either going to precipitate out lead 2 fluoride or magnesium 2 fluoride. And if we want to know which one is going to precipitate first, remember we said the one that has the lower KSP value is less soluble, therefore that one would precipitate first. So here the magnesium fluoride, because the KSP value is lower, it's to the -11th, would precipitate before the lead 2 fluoride would. So here is essentially what we are looking at doing is we have our base equation for both of these because they're both a +2 compared to fluoride's -1. So it should end up producing one of the metal ions and then 2 of the anions. So whenever this is set up in KSP, we would have the cation raised to no power multiplied by the anion squared to get our KSP value. And this value is for a different substance, but just to show you how this process would work. We would need to figure out what is the concentration of fluorine. So what is the concentration of the anion at which each of these would precipitate. Sorry, it's not clicking. So here are two dissolution equations. We have lead 2 fluoride would make 1 fluoride or 1 lead and then 2 fluoride ions. Same thing with magnesium fluoride. It makes 1 magnesium, 2 fluoride ions. KSP equations are going to look very similar. So it would be the concentration of lead times concentration of fluorine squared. If we plug that in, so we know it gave us that lead's concentration was the 7.0 times 10 to the third. We know the KSP for lead 2 fluoride. So if we divide by the 7.0 times 10 to the third, that would give us F squared, and then we would take the square root. So the fluoride concentration for this to precipitate out would end up being 0.010 molar. We would do the same thing for the magnesium fluoride. So here's our KSP equation. Looks very similar. We would plug in the KSP for magnesium fluoride and the concentration for magnesium. Yet again, we would divide by the 7.0 times 10 to the third and then take the square root. And we would get fluorine's concentration for this to precipitate would have to be 0.00010 molar. So that means that the magnesium fluoride is going to precipitate first, and it can precipitate anywhere between that 0.00010 molar and less than 0.010 molar, because if it reaches that 0.010 molar, the lead is also going to start to precipitate. So we would have to find a fluoride concentration in between those two to be able to precipitate out the magnesium fluoride, but not the lead 2 fluoride.